Okay, we started off here knowing the formula. They even gave it to us here. Volume equals, for of a cylinder, pi r squared h. The area of the base, and the area is a circle, so the area of the base times the height. And then here's our right circular cylinder. Let's draw the two bases, and then we have the radius and the height. Just sketch those in, because those are things that I think are changing. And so let's see, what are we given? The radius is decreasing. So dr dt would be -2 inches per second. And its height is increasing. So we know that dh dt would be +5 inches per second. And so what are we trying to find? It says when the radius is 4 inches and the height is 6 inches, how fast is the volume changing? So how fast? Well, that's a rate. So that tells us calculus. That tells us derivative. So the volume changing. So we want dv dt when the radius equals 4 inches and the height equals 6 inches. So far, so good? So now, what's our next step? Take the derivative. That's just about always the right answer in calculus here. Take the derivative, both sides with respect to time. What rule are we going to have to use? Product rule. So dv dt equals first times the derivative of the second plus the second times the derivative of the first. So 2 pi r dr dt. And what do we do next? Just plug it in. Just start plugging stuff in. Pi. Yes.
Can you leave pi out of it and do the brackets without it?
You sure can. Yeah, you could definitely pull out the constant. We could have done, let me see right over here, if we could pull out the pi, well then we could just take first times the derivative of the second plus the second times the derivative of the first. And then do you see how that's exactly the same as if we would have then, you know, if we distribute that pi, whoops, sorry, you get exactly the same thing that we had. So it doesn't matter which way you do it. You can either pull out the constant, or you can leave it in and treat it, you know, as the first factor. Okay, so then when do we plug this in? Let's see. Just plug that all in. Well, let's see. You can. Did you end up with -16 pi? Did we do that? Okay. So times 4 squared times 5 plus 4 times 6 times -2. And we get -16 pi inches cubed per second. Okay. And that would be an exact answer. And you want to leave them exact unless they tell you round to the nearest tenth or hundredths or thousands. But then otherwise you'll just go ahead and leave it exact. Delta Math, I think a lot of those problems have you, I think they had you round those, didn't they? They have you use your calculator. Round those, but okay, so that was number 6. So let's look now at number 7. Oh, the cone problem. This is in every calculus book. There's always a related rates cone problems. We have an inverted cone. Okay, we have a cone inverted cone that's leaking. Let me sketch. Let me get a piece of paper here, and it's by inverted they mean it's going to look like an ice cream cone. Can you see that? Okay, maybe I should. I'll do that darker. So our inverted cone, and let's see, we have the radius, and we have the height. And what do we know? We know the formula, and they were nice enough to even tell us 1/3 pi r squared h. Anything that comes to a point, pyramid, cylinder, is always 1/3 the area of the base times the height. The volume is 1/3. So it's still the area of the base times the height, but then it's 1/3 of that. So we know this. Let's see, what are we given? Inverted cone is leaking water at a rate of 1 cubic centimeters per minute. Well, what is that? The derivative of the volume. The volume is changing. As soon as it says rate, you know it's a derivative. And the units alone can tell you. Cubic centimeters per minute is the volume. So dV dt would be -1 cubic centimeters per minute. The cone has a height of 9 centimeters and a diameter of 6 centimeters. Find the rate at which the water level is dropping when the height is 3 centimeters. I'm going to read through the rest of the problem. When the height is 3 centimeters, so I'm just going to go ahead to what we're trying to find. What are we trying to find? Find the rate at which, so we want to find the derivative, the water level is dropping. So what's changing? dH, the height. What is dH dt when the height equals 3 centimeters? Now the cone problem is a little bit different than the other problems in the fact that the cone, I'm going to look at just this triangle here, this section. What did they say the radius of this was? Well, they told me the diameter was 6. So divide that by 2, so the radius would be 3 centimeters. Now that is not changing. You see, that's rigid. That's the shape of the cone. And then what is the height of the cone? 9 centimeters. That's the height of the whole cone. But our water in here, what do we have? Is it water? Yeah, we're leaking water. The water is going to be in this cone, and it's going to have a height, and it's going to have its own radius. And that's what's going to be changing. You see, those values are going to be changing. These are set. You see how those values are set? Well, remember geometry. What kind of triangles are these? What kind of, that big triangle and this little triangle are, well, they're both right triangles. Are they congruent? Are they exactly the same size and shape? No. What's the other word? They're not congruent, but they are similar. You remember that? Those would be similar triangles. So we could set up a ratio here. The ratio of, I don't know, a lot of different ratios, but R over H. Move this up here. What would R over H equal? 3 over 9. And I'll show you where we're going with this in just a minute here, but we're just figuring out what we know here. Well, let's see. Well, this would equal what? 1/3. R over H would equal 1/3. So if I cross multiply here, I get H equals 3R. What if I solve that for R? I could divide both sides by 3. I could get R would equal 3 over H. I'm going to look at this formula. The volume equals 1/3 pi. Okay. Yes. Thank you. Yes, thank you. The radius would equal H over 3. Well, I want to look at the formula, because in this formula right now, we would have to do product rule, which we could do, but this would be so much easier if we didn't have to do product rule. And look at what we're given and what we're trying to find. We're given dV dt. We're given about the volume, sorry. We're given about the volume, and we're trying to find the height. Do we need anything about the radius? You see how we're not given anything about the radius. We're not trying to find anything about the radius. So let's take that R out of the formula, and let's put in H over 3 in its place. You see, I could take that R out and put H over 3 in its place. So now we have 1/3 pi times, well, H over 3, I'll just write it out, H over 3 squared times H. So this would equal 1/3 times pi times H squared over 9 times H. Just see, I'm just multiplying that out, get rid of the squared there, squaring the H over 3. So this is going to be pi times H to the cubed all over 27. All over 27. That's my volume for this problem. That's going to be so much easier to work with. So now let's take the derivative of this. Now we have a new formula for this problem. And let's see, we're going to have dV dt equals, bring down the 3 pi over 27 H squared times dH dt. So much easier. We didn't have to do product rule at all. Question?
Why didn't you leave the H on the top? Like, why did you just take it off?
Where?
Like, you went from pi H over 3 over 27, and then below it, we did 3 pi over 27 times H squared.
Okay, I mean, you didn't like the fact that I don't have that in the top. There we go.
Yeah, I see that. So you can just, like, swap it whenever.
Yeah. I could have just written this pi over 27 H cubed.
Okay.
If that's, but yeah. Okay, so let's see. So what can we do here? This would be 1/9. No, that's good to ask. So dV dt equals, I don't know how we want to write that, pi over 9 H squared dH dt. Now let's just start substituting. Do we know dV dt?
Yes.
Yep. So -1 equals pi over 9 times, let's see, what is H? 3. They told me that they wanted to know when H was 3, when the height was 3. So this would be 3 squared. I'm running out of room. So this is -1 equals pi times dH dt. So dH dt would equal -1 over pi. And let's see, that's what we wanted to find. The only thing is I better get my units here. So the height is dropping. The height is decreasing. It's 1 over pi. And what are my units? Centimeters per minute. So the height is dropping at -1 over pi is an exact value, centimeters per minute. So that's a cone problem, an inverted cone problem. Does that make sense? Do you follow that? So whenever there's an inverted cone problem or a cone problem, look to see if you can get the formula, rewrite that formula in what you're given and what you're trying to find. So we wanted to pretty much get rid of the R. We wanted to get rid of the R because that wasn't given, that wasn't what we were given, and that wasn't what we're trying to find. Okay, well let's look at another one then. What's next? I wanted to look at the homework then. Let's go to the homework. Circle number 4, I'm going to have you do that one. That's a sort of, that's an easier one. The only thing is, let's write down the formula. What's the formula for volume of a cube? S cubed. Side cubed. Side times side times side. Yeah. Okay, well let's look at number, I just want to do 2 more problems, 5 and 6. We have time, yep. So I'm going to just do these with you here. Number 3 will be one of your homework problems, but then let's do number 5 and number 6. Number 5, let's read through this here real quick. We have an aircraft is climbing at a rate of 30-degree angle, at a 30-degree angle to horizontal. How fast is the aircraft gaining altitude if its speed is 500 miles per hour? So let's try to draw this. We're going to have horizontal, and then we have an aircraft that's climbing at a 30-degree angle. Now that 30-degree angle is not changing. It's staying at 30 degrees. So that's, I'm not going to even put a variable in for that. That's constant. That's staying the same, 30 degrees. So we have our aircraft is climbing. And let's see, let's see what letters I used before, but what do you want to use for this one? How about on a Z? We'll use Z for that, the airplane that's climbing. How fast is the aircraft gaining altitude? Well, altitude would be the height. How fast is that height changing? Well, y would make sense there. If we call that y, the height. Okay, so what do we know? Look at what we have on our figure there. Out of that information, what do we know? What formula do we have? Could we come up with for this? A right triangle? We couldn't really even use Pythagorean theorem with this because we don't know anything about this other side. And we don't care to know anything about it. They're not asking anything about it. What trig function could we set up with this? That 30 degrees, that y, and that z. Which trig function would that be? Or? Sine. Yes.
Yeah. I even did it in my head. Opposite over hypotenuse.
Yes, that's, someone said something, that was good. So sine of 30 degrees equals y over z. So that's what we know. Well, we could go even further. What is the sine of 30 degrees?
cycle or something.
Right, 1/2. Starts with 2.
0.5. So 1/2.
1/2.
From our circle.
My first year.
Remember, 30 degrees is just pi over 6, if you're better with that. But sine of 30 degrees would be 1/2. So we could just say 1/2 equals y over z. Or we could even say 2y equals z.
Oh, I don't know how that happens. Just
Cross multiply. That's it. I'm just trying to make it simpler. Whenever you can get rid of fractions, it's simpler. Okay, so we know we got down to a pretty good formula here that's connecting everything. So that's what we know. And let's see, what are we given? Let's read through that again. Aircraft is climbing at a 30-degree angle to the horizontal. We already have that in there. How fast is the aircraft gaining altitude if its speed is 500 miles per hour? What am I going to label that 500 miles per hour?
Velocity.
Is it dy or dz? dz. dz dt, because here's the airplane. The airplane's traveling here. So dz dt, remember the derivative is the rate of change. So the rate that z is changing. dz dt equals 500 miles per hour. And we are trying to find, it says how fast is the aircraft gaining altitude. So we're trying to find a rate, dy dt, you got it. dy dt equals question mark. So let's look at our formula. Now we have to just do our calculus with this. We have to take the derivative of both sides of that with respect to time. So let's see, we will get 2 dy dt equals dz dt. Just taking the derivative of both sides. You see where I get that? Yeah. I'm just using my simplest formula that I have in the know. And let's plug stuff in here. 2 dy dt equals 500. So divide by 2. We get dy dt equals 250. What units here? Miles per hour. So the altitude is changing, it's increasing at a rate of 250 miles per hour. Time for one more. Pretty fast. Yep. Okay, one more. I thought we have one more in us. Okay, last one. This is another one of those. Every calculus book has a man, well, it's always a man, usually, walking from a lamppost. There's a lot of lampposted calculus books here, but so we have a lamppost. So here's our, I'm not a good artist, so I label everything. There's my lamppost. A lamppost. And we have a man, a 6-foot tall man, walking at a rate of 5 feet per second away from the lamppost. That is 22 feet high. So this is 22 feet high lamppost. And let's see, we have this man that's 6 foot tall. And he's walking away from the lamppost. So let's see, if we label, I don't know. We see how we can make a triangle out of this? You can't see anything. Okay. So I'm going to make a triangle out of this. And let's label this X. From here, he's walking this way, so we'll label this X. I don't know, let's call this length Y. I'll go ahead and let that whole thing be X plus Y. There's different ways we can label this, but this might be the simplest. So no, I'm going to hold off on the no for just a minute. And let's see, what are we given? A man, 6 foot tall man, walks at a rate of 5 feet per second away from a lamppost. So this is what's increasing here. This distance here is increasing. So we're given that dx dt is 5 feet per second. Given, find. I keep wanting to say prove, but given, find. At what rate is the length of his shadow changing?
What?
So what are we trying to find? Where is his shadow? Y. Here is his shadow. Good. So we want to know what is dy dt when he is 60 feet away from the lamppost. So what would that be? Is it y equals 60? X equals 60. When x equals 60 feet. It says he's 60 feet away from the lamppost. So we want to know the rate that his shadow is changing. So we want to know dy dt when x equals 60, when he is 60 feet away from the lamppost. Well, we skipped over this no. Look at that figure. Is Pythagorean theorem going to help us here? No. We don't have area. We don't have volume. No other geometry. Do you see the similar triangles in here?
Yes.
You see the similar triangles, the small triangle with the large triangle? So we can set up a ratio again. Let's see, I could set this up, different ways we can do this, but how about 22 over x plus y? What would that equal? Good. So I'm going to look at, there's the large triangle, 22 x plus y. And then the small triangle here is 6y. Sorry, I can't see that. Did you see where we get that? Remembering your geometry? There's the large triangle, there's the small triangle. So there's different ways we could set that up. But so we just did 22 over x plus y equals 6 over y. What do you want to do next? Cross multiply. Cross multiply. So let's see, this is going to be 6x plus 6y equals 22y. So I don't know, let's see, subtract 6y. Might as well simplify this. 6x equals 16y. I don't know, we could simplify that more. How about we just take the derivative? We take the derivative with both sides with respect to time. So this will be 6 dx dt equals 16 dy dt. So let's see, what am I trying to find? dy dt? Okay, so let's just substitute 6 times 5. be careful, I don't want x there, I want dx dt. So yeah, dx dt is 5. So 6 times 5 equals 16 dy dt. Divide both sides by 16. Let's see, 3, 8. So 15/8 dy dt. We didn't even need that x. And what units are we? Feet per second. So his shadow is increasing at almost 2 feet per second. Okay, his shadow is... You're done? Okay, that was an awful lot. So there's 4 problems then. 4 problems. I put them on